A centrifugal pump is connected to a piping system as shown below. The pipe is 5 centimeters in diameter and has a roughness epsilon of 0.5 millimeters. The two valves are identical and have minor loss coefficients of 1 when fully open and 20 when 50% open. With both valves fully open, the pressure gauge reads 250 kilopascals. When both valves are 50% open, the flow is 355 liters per minute. The pump curve can be represented by a parabola. The free surface in the tank is at the same elevation as the pipe exit. Let nu equal 10 to the minus 6 meters squared per second and rho equal 998 kilograms per cubic meter. Determine PA if the first valve is fully open and the second valve is fully closed. Neglect minor losses which occur on the suction side of the pump. So we have a schematic diagram of this apparatus given as well, so we're going to make use of that as our given information, and we'll be adding some other labeling to this as we go along. So here's the reservoir. Water gets drawn out of the reservoir into a centrifugal pump, and we're ignoring losses on this side of the pump as we're told to here. Discharge of the pump will be at a relatively high pressure. Flow goes through a valve, past a pressure gauge, through an identical valve, and then eventually spews out to atmosphere. And each of these sections is 25 meters long. Now what we're asked to find is if we close this valve, what does this pressure become? So let's make a note of what we're asked to find. So find, so PA when the second valve is closed. And we'll keep a list of assumptions as we go through this. And we'll begin our analysis down here. So this is a piping system which includes a pump, and we need to include the characteristics of that pump in the analysis of this piping system. Now what are we told about the pump? Well, it's a centrifugal pump, so we know generally what the pump curve looks like, but this gets a bit more specific here, and it says the pump curve can be represented by a parabola. So it's very useful for systems where we're dealing with a pump and a piping system working together to draw a pump curve and a system curve on the same axes. So I'm going to choose pressure on the vertical axis and velocity on the horizontal axis. Quite often we use flow rate for the horizontal axis, but they're really interchangeable. If we know one, we know the other. So we're told the pump curve is a parabola. It's a centrifugal pump, so it's going to look something like that. And in this case, this is a parabola. So delta P pump is going to be some constant minus some other constant times V squared. So that's the pump curve. Now what we also want to plot on the same diagram is the system curve. And the system curve, remember, is going to be a parabola that looks something like this. So go back to our system and note a couple of things about it. Note that the beginning and ending elevation is the same, and the beginning and ending pressure is the same, both atmospheric. That means the fixed system pressure is 0, and we only have the variable system pressure, the portion that is dependent on the velocity or the flow rate. So when we go down here to sketch the parabolas that represent the system curves, they go through the origin. There's no fixed system pressure. Now the problem describes two different operating conditions. One, where we have the valves 50% closed, and a second when the valves are fully open, which will have an increased flow rate. So back here, the valves are partially closed, so the flow rate is restricted. Open up the valves, flow rate increases. So we have two operating points. This one is for the valves open. And I'm going to label these operating points 1 and 2, and we'll be referring to those as we go forward here. Now, what we're asked to find here is the pressure when the second valve is closed. So just take a look at this. This valve is closed. There's no flow through the pipe. So the pressure here will be the same as the discharge pressure of the pump, which, because this side is atmospheric, is the delta P across the pump. So what we're really looking for here is that constant A in the pump curve. Because we go back to our diagram, when the velocity goes to 0, the pump pressure goes up to this value. And that's the value of A. So this A is what we're solving for. So in order to figure out what that A is, we need to consider these two operating points. If we can figure out the coordinates of these 2 points, and by coordinates I mean the velocity and the pressure for each of those 2 points, then we'll have 2 points along this curve, and we can use those 2 points to solve for A and B. And it's A that we're really interested in. So that's the approach we're going to take here. So we're going to start off by looking at operating point 1. Now, what do we know about operating point 1? Well, it says with both valves fully open, the pressure gauge reads 250 kPa. So that pressure gauge is right here. So we know that from here to here, the pressure goes from 250 kilopascals down to 0. And we know the length of the pipe, we know the minor loss coefficient for that valve, so we should be able to figure out the flow rate from that information. So that's what we're going to do. We're going to first of all just look at this segment of the pipe to figure out the flow for that operating point 1. So I want to do some labeling on this diagram. I'm going to call the surface of the reservoir point 1, position of this pressure gauge point 2, and the exit point 3. But to begin, we're going to write Bernoulli's just from 2 to 3 to figure out the flow rate. So we're talking about operating point 1 here, and we're writing Bernoulli's equation from point 2 to point 3. So P2 plus rho V2 squared over 2 plus rho G Z2 equals the same thing at point 3. So that's Bernoulli's equation. But we also have losses, so we'll put a rho V squared over 2 here and include the frictional losses, FL over D, plus any minor losses that occur between points 2 and point 3. Now we take a look at our diagram, and we'll be able to make some simplifications to that equation. Now, first of all, we've brought out Bernoulli's equation, so we should make some assumptions. This is assuming steady flow. It is incompressible, so that density is a constant. It's uniform at the inlets and exits. We're just using a single velocity to represent the flow rate. And the temperature is constant as well, and there's no heat transfer. So all of those things are included in Bernoulli's equation. So if we go back and we think about point 2 and 3, point 2 and 3 have the same velocity because the pipe diameter is the same. They also have the same elevation. And point 3 is at atmospheric pressure. So all of those things can be applied to this equation as assumptions. So the velocity at 2 and 3 are the same. So that goes. The elevation at point 2 and point 3 are the same. So that goes. And the pressure point 3 is atmospheric. So that goes. So what we have left is P2 is equal to rho V squared over 2 times FL over D plus the minor loss coefficient of the valve. Now, if we take a look at this and think about what we know and what we don't know, this is a problem where we know the pressure but we don't know the velocity. So it's an unknown flow rate type pipe flow problem. So we have to set up an iterative solution because this friction factor is dependent on this velocity. So that's what we'll set out to do here. So we'll begin by putting all the numbers we have into this equation. So we know the pressure gauge is reading 250 kPa, or 250,000 pascals. We know the density is 998 kilograms per meter cubed. That's divided by 2. The velocity is unknown, so we leave that as v squared. F is not known, leave that as f. And the length is 50 meters, and the diameter is 0.05 meters, and then plus 1. So we can calculate out everything that we have so far there, and we get V alone on the left-hand side, 501 in the numerator, and in the denominator 1000 F plus 1. And all of that is to the 1/2 power. And I'll call that equation 1, and we'll need that in our iterative solution. So the friction factor in here is a function of two things: relative roughness and Reynolds number. So the relative roughness, epsilon over d, the roughness elements were 0.5 millimeter high. The pipe diameter is 50 millimeters. So the relative roughness is 0.01. The Reynolds number is equal to the velocity times the diameter divided by the kinematic viscosity. So our velocity, our diameter, 0.05 meters, and the kinematic viscosity was given to us as 10 to the minus 6 meters squared per second. So the Reynolds number is 50,000 times the velocity, and that is equation 2. So we set up our iterative solution: friction factor, velocity, and Reynolds number. Velocity is going to be calculated from equation 1. Reynolds number is going to be calculated from equation 2. And the first time through this, we'll be putting in a guess for the friction factor. So because this is a rough pipe, the most effective guess for this friction factor is the so-called fully rough value. You can just put an extremely large number like 10 to the 99 into the Colebrook equation. And if you do that, you'll get an F value of 0.03790. Using equation 1 with that F, you'll get a velocity of 3.589. And using that velocity in equation 2, just multiplying it by 50,000, you get a Reynolds number of 179,429. Now for the second iteration, we no longer guess F, we get a better estimate of it from this Reynolds number. So that Reynolds number and this relative roughness go into the Colebrook equation, and we get an F of 0.03824, and that gives us a velocity a little bit lower, 3.573, and a Reynolds number a little bit lower, 178,657. Take that Reynolds number and our roughness into the Colebrook equation again, and we find out that at least to these 4 significant figures, we get exactly the same friction factor. But I carried a couple extra decimal places in my calculator and recalculated this, and it comes out to the same thing actually, 0.573. So this is certainly converged. So we have a velocity at operating point 1. So if we take a look at our system curve, operating point 1, I now know the velocity of that, but I need to figure out the pressure. So in order to do that, I'm going to have to write Bernoulli's equation again, all the way from point 1 to point 3. So we're still looking at operating point 1, but now we're going to write Bernoulli's from point 1 all the way to point 3. So rho 1 V1 squared over 2 plus rho G Z1 equals, all the way to the end, P3 rho V3 squared over 2 plus rho G Z3. So that's basic Bernoulli's equation, plus the losses as before. So we have rho V squared over 2, frictional losses FL over D, plus minor losses. So that's all of the losses. And then finally, because now we're going all the way from 1 to 3, we have a pump in between those 2 points. So we need to put minus delta P pump on the end. So again, we can apply similar assumptions as before. We begin and end at atmospheric pressure. The reservoir is large, so that velocity is very small. So I'll go back and add that to my assumptions. So a large reservoir. And that's what makes V1 equal to 0. And we should also say here there's no elevation changes. So that means all of the z's are the same. So that allows me to cancel out these two terms as well. V3 we need to keep because the fluid still has some kinetic energy leaving the piping system. So now I'll bring this delta P pump over to the left-hand side because that's what I'm solving for here. And take a look at what we've got left over. Everything else scales with rho V squared over 2. So we have our frictional losses, FL over D, plus the summation of the minor losses. And then we need to remember this, and we can include that just by putting plus 1 there. Now, because we solve for the velocity up here, and we have a friction factor, we know everything on the right-hand side of this equation, so we can get our delta P pump. So we'll put these numbers in, 998 kilograms per meter cubed, divided by 2, velocity 3.573 meters per second, and that's squared. Friction factor 0.03824. And our length of pipe, remember now we have all 100 meters of pipe because we're considering the entire system. Diameter is still 0.05 meters. It's important when we calculate this L over D to make sure you have the length and the diameter in the same units. The minor losses, there are 2 valves now that are both fully open, so that's minor loss coefficient of 2, 1 for each one, and then plus 1 for this kinetic energy term that we also are including. So that all gives us a delta P of 506.3 kilopascals when we calculate that out. So now we know everything we need to know about operating point 1. So we'll just give that here. So operating point 1 has a delta P pump of 506.3 kPa and a velocity of 3.573 meters per second. So we go back. What we've done is calculated the coordinates of that point. We know the velocity and we know the pressure. So that point is nailed down. We need to do the same thing for point 2, and we'll have enough information to define this curve and figure out A. So we go on now to consider point 2, operating point 2. Now this one is a little bit easier because we know the flow rate. The volume flow rate was given, so we know that, and we're not going to have to do any iterative solution. So we can make use of the Bernoulli's equation we already have written from point 1 to 3. So I'll just rewrite that here. So frictional losses, minor losses, and kinetic energy. So that's the Bernoulli's equation that applies here. But now there's no iterative solution required because we know the volume flow rate. We were told that it was 355 liters per minute. So we convert this to SI units. That 5.916 times 10 to the minus 3 meters cubed per second. The velocity is q over a. So our 5.916 times 10 to the minus 3 meters cubed per second is the volume flow rate. Divide by the area of the pipe, pi by 4, times the diameter, 0.05 meters squared. And that gives us a velocity 3.013 meters per second. So notice the velocity has decreased from 3.573 to 3.013 because the valves have been partially closed. So now we need also the Reynolds number. So that's Vd over nu, but with a new velocity. So 3.013 meters per second. Diameter 0.05 meters. Kinematic viscosity 10 to the minus 6 meters squared per second. And we get a Reynolds number of 150,667. And so notice we know what the Reynolds number is, no iteration required. Colebrook equation with that Reynolds number and our relative roughness, which is still 0.01. We get a friction factor 0.03830. So notice the friction factor really hasn't changed very, very much. A little bit larger than it was in the previous case because the Reynolds number is a little bit smaller. So now all of that information goes directly into this equation to calculate our new delta P pump. So delta P, density 998 kilograms per meter cubed. Velocity 3.013 meters per second squared. That's over 2. Friction factor 0.03830. L, full 100 meters of pipe. D, 0.05 meters. Plus the summation of our minor losses. Now notice the valves are 50% closed now. There's 2 of them, so that adds up to minor loss coefficient of 40 and still the kinetic energy at the exit. So all of that tells us that delta P of the pump is now 532.8 kilopascals. So that tells us our second operating point. So operating point number 2 has a delta P pump 532.8 kPa and a velocity of 3.013 meters per second. So notice that's the second point here. It's the coordinates of the second point, V and P for the second point. So we know where those 2 points are. Now what we need to do is use those 2 pieces of information to calculate A and B. So I'll just recall what this pump curve looks like. And we can look at operating point 1 and write that equation with what we know about operating point 1. So 506.3 is equal to A minus B V squared. And that V is 3.573. And rewrite it again, but at operating point 2, 532.8 is the pressure. A minus B times velocity, which has reduced. So I have 2 equations with 2 unknowns. So I'm going to subtract these 2 equations. Left-hand side, I get minus 26.5. A minus A disappears. Over here, minus B, that squared minus this squared is 3.688. So this gives me a B equal to 7.185. So I can take that B and put it into either one of these equations to solve for A. I'm going to use the first one. So therefore, A is equal to 506.3 plus 7.185 times 3.573 squared. And so that works out to a value of A of 598.0, and that will be kilopascals. So therefore, the pressure at A is equal to 598 kPa when the second valve is closed.